Welcome to Purdue University College of Science Superheroes of Science podcast. I'm Stephen.
And I'm Sarah. We will be discussing anything and everything related to the science classroom and interviewing scientists.
Because as we know, scientists are the superheroes behind the science.
So join us as we learn about the scientists and explore current trends in K-12 science education. We have Corey Thompson with us today, and Corey is an assistant professor in the Department of Chemistry here at Purdue University, and he has agreed to sit with us and talk a little bit about some of the research that he does, and we are excited to learn more from him.
You know, you're the first release, right? You are going to be the person that set the bar. Since you said you were nervous, I got to throw that out.
My goodness.
Well, it's because this is the superheroes of science.
Yes.
Who better are we going to introduce to start with than you?
I'm not a superhero. But
What?
Corey.
Oh, Peter Parker didn't think he was either. It's all right. It's all right. The ones that don't know it are the best superheroes.
I'll take the Punisher title. That's my best Marvel.
We started the superheroes, and I think we've talked to you about this before, but students don't think superheroes are real.
Mm-hmm.
And students don't think that scientists are real.
Mm-hmm.
But you are very real. You're sitting here with us talking to us.
And you're very super.
You are super.
I guess.
Dude, you're my hero.
I'm not sure.
So, I mean, you know.
You guys are my heroes.
Oh. Well.
I mean, you interact with more students than I do, probably, on a yearly basis. So.
Okay.
We do corrupt a lot of kids. I mean, yes, teach a lot of kids.
That's what I say when I'm in class. I go, hey, welcome to your first day of class with Professor Thompson. I'm here to destroy your minds.
Oh, that's a good
And they all
intro.
start
I like
laughing.
it. Oh, good. Well, Corey, we are interested to know, how did you get interested in science? Where did you start?
So, growing up, I wanted to be actually a cardiac surgeon. Mainly because of my sister, right? And that's what she wanted to do. And she's like 4 years older than me. And so I went to University of Florida for undergrad and started off a pre-med or a microbiology major. Of course, I hated biology because of looking at microscopes, 60 microscopes in 1 hour, trying to figure out what the cell is. But the other reason why I got out of sort of pre-med is because of shadowing a doctor at the hospital. And so I used to shadow doctors that works on the cardiac wing, and one of the doctors had a friend that was going into surgery, and he was supposed to do a total hysterectomy on someone, and so I get in there, and the first thing the doctor says is, hey, we don't vomit in here in the surgery room, but if you do, we have this huge garbage can, that's what it's there for. And so I was in there. Of course, like I said, this is before they had the curtains covering the people's faces.
Right.
And the first thing they do, the nurse pulls out this big old ball of something and just drops it on this metal table, and blood is splattering everywhere.
Oh my goodness.
And I was like, oh my God.
Oh my gosh. Have you ever, and this is your first surgery?
First time sitting in on a surgery. I never had surgery myself. I mean, I've been sold and stuff like that, but never had to have surgery. And I've never seen this much blood probably in my life. And she takes this ball out and just drops it on a table like it was like a basketball or something.
Oh.
And just blood splatters everywhere. And the first thing I do is just vomit.
Oh no!
Yeah, and the doctor's like, "Oh, there he goes," and he pushed the garbage can over there, and I'm vomiting in the garbage can, and the nurse is laughing.
The nurse,
the doctor's laughing. Yeah, she's looking, she's laughing, and he knew this was going to happen, but I think she did it on purpose.
Oh my goodness!
And from that day on, I just said, I don't think this is for me. So.
Good to find out.
Those two things, shadowing the doctor, as well as hating biology. I went to my advisor, and I told her, I said, hey, I hate biology. She was like, well, you have to take, you have to pass genetics. Mm-hmm. And I hated genetics. And so she was like, but you're really good at chemistry, and so you should think about transferring to chemistry. And so she called the chemistry advisor, and he said, sure, we'll take this guy. And from there, I just kept going with chemistry. And that's where I am here today, I guess.
Yeah. So you went, you decided, okay, chemistry, and then...
I kind of just went with it, you know, because I wasn't sure for that point. I knew I hated biology, and so I didn't want to be a surgeon. So, and she said I liked the chemistry, so I listened to her, and I just kept taking the classes, and I actually enjoyed it, and so I just continued on with it. From undergrad to grad school, you know, I took a year off because I have friends that were going to graduate a year later. And so I stayed there in Gainesville, and then I was delivering pizzas for Domino's.
Wait, after you graduated?
After I graduated.
Okay.
I graduated in 2006. I don't know if I should say that, but I delivered pizza for Domino's for a year. I enjoyed it, and then during that year, I think I went to one of my undergraduate research advisors' house and delivered pizza to him, and he was like, "What are you doing here with a bachelor's in chemistry?" And I was like, "I'm earning money and delivering pizzas." And he said, "You know, you're too good for this. You should consider going to grad school in chemistry. You're really good with your hands and you understand the subject." And so he said, "If you apply, you know, I will pay for your application fees or what have you." And
wow.
From that day forward, that's how I got into grad school, and I just continued on from there.
When you said that the other day when we were chatting, what I liked the best about that, you're where you are today because someone believed in you.
That is true. That's very true.
And that's awesome. And that shows how important it is to me. It shows how important it is that when we believe in people, we have to let them know.
Yeah.
You know, hey, you can do this. I don't know how many times that I've worked with kids and programs and stuff, then later I've seen them, and they always stop me. And that little encouragement, being able to encourage them to go live up to your potential and do something, is so important.
It's very important. And so what I try to do in my research group, they may not believe me, but, you know, we tend to always give people negative feedback because we always think they can be better. And so we always say, hey, you know, this is what you're doing wrong. This is how you can improve. But when I meet with them individually, I try to say, hey, you know, this is what I like that you do, to let them know that they're doing something good. But this is what I also think you should try, you know, so they get to see that they can always still improve. And so I always throw the positive in there, because if you don't give them positive feedback, they always think they're not good enough. And so, and that's something I took away from, you know, that research advisor. He was always there, you know. He convinced me to go to grad school. He's the first, he was the first chemist professor I did research with. And then when I went to do a postdoc, you know, he was giving me advice. Even for a faculty position, he gave me a lot of advice for my interviews. And so I still talk to him to this day, see him at conferences. And so, you know, he played a huge role.
What research did you do?
As an undergrad? Oh, man, I did so many different types. So my first year, I was doing some environmental engineering research. And so basically, I did that for the first 2 years. And what we do is we go out to landfills. So I was picking up a lot of trash. So basically, we go out to landfills, or we go to different playgrounds, and we was testing the dirt or the mulch. And we were seeing what happens when it rains, and does that rain somehow leach something out of that mulch or that landfill? And then will it be hazardous to the earth, one, or two, to the kids when they pick up some of this stuff when they're at the playgrounds?
Right.
And so I did that my first 2 years. I was in the engineering department, like doing research with them. And then in grad school, I totally switched fields, and I started doing solid state chemistry, kind of like what I'm doing today now in my research group. And what I, you know, is totally unique, where you actually just taking powdered elements from the periodic table, and then you're mixing them together using a motor pestle, and then you bake them at very high temperatures. Like, I mean, we're talking about 1,700 degrees Celsius, so this is like 3,000 Fahrenheit and so forth. And then afterwards, after we crushed them, and then we test them, looking at their structure and their physical properties. And so, as a graduate student, we was looking at magnetism, and so we was trying to see if these things will have unique magnetic properties for different applications. And so we was focusing more on like looking at magnetic refrigeration technology, because it's predicted that magnetic refrigeration will be more efficient than what we currently use today. And so,
what do we currently use today?
So we use this gas compression type technology
okay.
for our refrigerators, and so now we not long ago we used to use these sort of hazardous gases to do it. Now we kind of got away from it, but they're still considered greenhouse, gas materials, and so a lot of people are now trying to get into this method of refrigeration, and it blossomed in the last decade. Because it's theoretically predicted to be more efficient, and so we have materials that are efficient, but the problem is they're expensive, or when you have them in this type of application, they tend to like degrade over time. And so that's what the research I did undergrad and grad school, and then now what I do, I kind of do the same stuff where my group mostly focus on magnetic materials, so we're more energy conversion, sort of storage. We're trying to develop new materials that are more efficient or actually cheaper for magnetic refrigeration. We also look at data storage and hard drives, so we're trying to make them faster, we try to make them cheaper, actually smaller as well. We also look at permanent magnets, so we can actually create cheaper permanent magnets, because now the most dominant materials have a lot of rare earth elements in their composition, and so we're trying to make it cheaper because China owns most of the rare earths elements. And then we also do other types of stuff like thermoelectrics, and so these are stuff that you use on a daily basis but you don't know, and so these are actually in your car seats. That's what cools them down, or heats them up or whatever in your car seats. We use them in space probes, so that's what keeps them powered for a long time in space. We use these thermoelectric materials, and so that's the kind of research we do. I know, it's a lot.
yeah, I'm trying to get my head around that.
Yeah.
You're so do you still, like, you're combining elements? I know what I've been up in your lab there last spring, and you had like all kinds of different elements in there.
Yeah. So we're solid state chemists. That's our title, but we're a subgroup of inorganic chemistry, which is the field. And mainly we're inorganic chemists because we work with almost every element on a periodic table. And so when you look in our glove box, and we have almost everything except actinides, because you got to get radiological training. But so we combine. It depends on what we're trying to make. I have projects where one student, he's doing a lot of rare earths, combining them with transition metals, but in his case, he's trying to make the rare earth content very small, so it can still be useful in a way, because we use a lot of rare earth elements because they have a large amount of magnetic moments or magnetic characters, so that's why they're so important for permanent magnets and so forth. But if we could take advantage of their properties and combine with transition metals to cheaper materials, they will still have this nice effect that we need for their applications. And so we're somehow still using them, but we use them in smaller amounts compared to what people have done in the past. We still do other stuff where we just have transition metal based materials like iron, cobalt, and nickel, and we don't have any rare earth elements there, so we do that type of stuff as well. And we're binding them to like sulfur and oxygen and aluminum and silicon.
Are you still like powdering them?
So we do
stuff?
different methods. In some methods we powder them up, press them into pellets. What you guys see is that we arc melt them, so we use a welder to actually melt these materials because they need very high temperatures to actually react, because these materials are very stable at very high temperatures, so you have to force them to react. So that's why we use the electric arc from the welder. In other cases, we could use low melting elements like tan or bismuths, where they melt at like 200 degrees Celsius, and they act as a solvent in the reaction, because we don't really work with solvents, and so they liquefy, and then they actually help mix your metals better together, and then you can slow cool it, and then you get these crystals that crystallize out as you slow cool it.
Oh wow!
So we do different methods, but we're still heating these things at 1,000 degrees Celsius or higher to make it work.
I know when the students came, I think they were really impressed that they were in a chemistry lab, but they were welding.
Yeah. Well, so it's a unique technique that I learned in grad school, and not too many people, actually a lot of engineers and physicists do it, but most people, when they do welding, you think about making cars, right? You welding two metals together and so forth. No one really uses it much for synthesis, like making materials. You actually use it to weld two things together. And so it's a technique that we learn, and I always try to show like people in elementary and so forth for high school that we actually do stuff with this to make materials, not only just to bind two sheets of metal together or something. And so I always give them a chance to like work around with it, and as long as they're wearing the safety stuff, they need special shades because if they don't, you know what happens.
And I don't know. I remember, heck, in high school, it took 4 years of welding. I welded at home, but I never would have thought using it for chemistry. I had no idea.
I never thought either until, my PhD advisor was like, hey, can you order this welder? And I was like, okay, we're making like, some car or something? I think that's the only thing I can think of. And he was like, no, we got to use this for synthesis. I said, what? Because, it was a new area. I never done it before. I never heard of using a welder to make actual materials, and so it's actually pretty cool.
So you have a welder, which is sort of what I think that's sort of out of the box for a chemistry lab.
Yeah.
But are there other pieces of equipment or ovens that you have that are the norm?
My lab has probably 19 furnaces
Oh my
or ovens, if you will, and we have various versions. It depends on how fast we want to heat the material, how long we want to heat it. Do we need to program the furnace? Like it needs to have a special protocol or procedure to get there. So we have furnaces that go, from room temperature all the way up to about 1700 degrees Celsius. And we have a box furnace or a muffle furnace where we could just, put things in there, heat them. Then we have two furnaces just in case like we want to actually heat materials but under inner atmosphere, and so we use like argon gas or nitrogen, or if we want to, like in some cases, if let's say we run out of iron but we have iron oxide in the lab, we could take iron oxide and we could just purge hydrogen through there and reduce it to iron metal while we're heating it. And so we don't necessarily have to buy the iron metal, which is actually more expensive than the oxide, because the oxide is kind of like a mineral or something coming from the earth. And so we could reduce things down to the elemental components in our lab, and then use them later for reactions and so forth. And then we have an induction heater, which is kind of, you can think of it as something being similar to a microwave, where we use the waves from applying some current in the coils, which these waves sort of get absorbed in some type of absorbing material. We use actually like a graphite crucible which absorbs these waves and it heats up, and then we can heat up materials under gas or vacuum. And this is another method that is kind of similar to arc melting or using a welder. The only difference is you could make larger amount of samples, whereas the welder is kind of limited. Smaller. So we have furnaces, of course, because that's what we do, and then we have glove boxes. Of course, we have to keep these elements under inert gas to protect them from oxidizing.
And when you say glove box, you actually mean the things we see on the sci-fi movies.
Yes.
You're not actually exposed to it. You have to reach through these long gloves and you're working inside this enclosed container.
So yes, so we get a lot of undergraduate students, a lot of graduate students who never worked in a glove box before, and so it takes a lot of practice, because when you're in there, sometimes you're in there for too long because you never used it before, and so we have students that will be in there for 4 or 5 hours, and
oh my gosh,
and they start sweating, and so we have a fan in the lab to keep it cool down.
Keep it comfortable.
Or usually I tell them, hey, work in there for about an hour, take a break, and then come back and get in there.
Now, when you're working does your hands sweat inside those?
Yeah, so your hands sweat. So we have ways to get around that. Typically, what we do is we powder ourselves. We powder ourselves, or we wear these thin light gloves over our hands, and then we powder our arms, and then we go in there. And then on top of that, we actually wear gloves on top of those gloves. To protect the surface of those gloves while we're in there, because you'll get powder dumped on there sometimes, and which makes it dirty, so you have cross-contamination. And so you don't want that. And so we actually wear gloves on there. So you have gloves on top of gloves on top of gloves.
Oh my goodness.
While you're working in the glove box. And so it gets very difficult to try to handle things. And so it takes practice, and over time you'll get faster, but it's kind of crazy. And then you got to worry about the pressure of the glove, the glove box, because you have gas in there, and so you have to worry about like sort of vacuuming that gas out to release it while you're inside, and so you have to fight against pressure. And then if you're weighing powders out there, you have to fight against static, and so so you'd be like weighing powders out there, you'll see the powder fly. You're like, oh my god. And so it's a mess.
I like that. Yeah, it's mess. So when students come, because you mentioned you have several grad students in your group and stuff, how many do you have, and do they have like their own research projects under you they're working on, or do you give them research projects? How does it work if students want to?
So that's a good question. So I have 3 graduate students right now and 1 postdoc, and then I have 4 undergrads, or 5 now. It's hard to tell because they tend to say yes and they tend to say no, but we get a lot. But
a postdoc just means someone who has a PhD.
Yes,
they have that degree.
So they have
whatever now.
So a postdoc is they have a PhD degree, and then they spend time. You're allowed to get training, additional training. They learn how to supervise, or run a group, and so that's what they're learning from you. So they're, they could do this to get additional training to go into, industry, or to go into academia to be a professor. But basically, they're learning new research. And then they're learning how to supervise and manage groups. They're writing proposals. They're doing all this other stuff that an actual professor will do, but don't get paid as much as a professor. And so that's what we call a postdoc. And then graduate students, when they usually come in our group, I have these brief 2-page, 3-page proposals on different areas that I've been thinking about. And so usually I give that to them, and I let them decide where they want to go. And when they come to me, they don't necessarily have to work on those projects I set the proposals on. They could come and just say, I just want to work for you because you're awesome, which I'm not.
Well, you're used to that.
And then they could design their own project if they want. They could just say, hey, I really want to work on like solar cells or something like this, but I know this is not your area. Can we somehow design some compound or material that would be useful for this application? Or they'll work on the proposals that I gave them, and they'll just say, hey, I want to work on this one. Now, once I figure out which one they want to work on, then we kind of work out a plan of action. And then I say, okay, well, these are the materials I've been looking at, and this is why. And I sort of give them a background of it, and I give them some articles to read. And then once they do that, we start hashing out which materials to actually focus on, or which elements to combine together that will probably give us the best properties for this application. And so that's kind of how we sort of have the lab designed up. I don't think every lab is that way, but for the most part, they get some research proposal to help them figure out like what we specifically know how to do. And then if they want to design a research project that we don't know how to do, but we kind of know how to do some of the different characterization techniques like X-ray diffraction, or looking at a thermal decomposition of materials like that, we have those instruments here in the department or in my lab, which will allow them to succeed. It's just trying to figure out the right material for that specific application.
Great. I think in addition to all of this, you also help with this Project Seed.
Yes.
And does Project Seed involve research?
Project Seed does. So Project Seed is this big organization, part of the American Chemical Society, and basically their goal is to sort of give high school students who are economically disadvantaged experiences that they normally wouldn't get at their home institution or in their surrounding neighborhoods. And so basically they come on campus or university and actually do research in a research lab with a professor, or they could do it with staff. And so they spend 8 weeks, and during that 8 weeks they learn a lot of things. Like they learn how to write a research report. They actually present posters at a poster session. They will have group meetings or individual meetings with the professor and a group, and of course they're doing regular research either on a bench or depending on which division or college it is, they can do engineering or science. And then they also get paid. So
nice.
that's a benefit. They get paid while doing this. And so it's a good opportunity for high school students. I mean, I never had this opportunity when I was a high school student.
Yeah, I didn't.
Or never heard of it.
Yeah, I'd never heard of that.
And so it's a good opportunity for students to do research on campus.
Well, given your role with that and the students that come in and do research, and then your role with your graduate students that are looking at projects and maybe developing their own research, what advice would you maybe give to a high school teacher that's interested in trying to start some sort of research with their students in a high school setting but isn't quite sure where to start?
Whew, that's a loaded question. The advice, I think it all depends on just. I would say I will reach out to the university. Like if you're unsure what you want to do, you can just reach out to the people on university campus and the professors or you guys, and you could put them in contact with the professors, and you could just say, hey, we would like to do some research in our classroom with our students. Can we design an experiment or some research that we can do here in-house? Or if they're local, that we could do in your lab, and somehow they could get that experience without the paid component of Project Seed. And I think it's very doable. I think you'll be surprised by the number of professors who's willing to do that. But it, it's hard to say. Like I would say for a high school teacher, they would have to reach out more than the professor reaching out to them. But I'm sure I would say that's my best advice. It may not be you guys know more than I do, but I would say if they're trying to design a research project and they're not sure which research project, just reach out to the professors in either Department of Chemistry, Biology, Physics, or EAPS, and engineering, to say, hey, we want to design something. What resources can you provide us, and can you help us design an experiment? And in all likelihood, I think you will find somebody on campus who is willing to help them. Of course, they could do the normal thing that we all do as professors, where we just, look in the literature
That's there even as a high school teacher. I think that's important because those are the new ideas. Those are the things. Well, Corey, thank you very much. We appreciate your time, and we're excited to roll this out. So.
Our first superhero of science.
Well, thank you for having me. I enjoyed it. It was fun.
Thank you for listening to our podcast.
If you love Superheroes of Science, be sure to subscribe, rate, and give a review on iTunes or your preferred podcast player. Be sure to join us as we add interviews of scientists and incorporate discussions of current trends in K-12 science.
Until next time, be super, and remember, you are someone's hero. Boiler up.
Hammer down.